Dear students, welcome to the course Groundwater and Hydraulics, Module 1, Groundwater, Session number 2. I am Raja Anwar Hussain, Assistant Professor, Government Engineering College, Raichur. Contents in this session will be learning about vertical distribution of subsurface water. Vertical distribution of subsurface water. Here in this figure you can see various zones. Number 1, soil water zone. Number 2, intermediate zone. Number 3, capillary zone. And the last one is saturated zone. Vertical distribution of subsurface water. Here, water in the surface may be divided into two major zones. Number 1, water stored in the unsaturated zone, also known as Vadose zone or zone of aeration. Number 2, water stored in the saturated zone for groundwater or gravitational moisture. In vertical distribution of subsurface water, you can see the various zones, that is soil water zone, intermediate water zone, capillary zone, and the last one is the zone of saturation. Zone of aeration. In this zone, there is a free exchange of air and moisture found between ground surface and water table. It can be divided into three belts, that is soil water, intermediate zone or vadose, and third capillary water. Whereas in soil water zone, water in the soil water zone exists at less than saturation except temporarily when excessive water reaches the ground surface as from rainfall or irrigation. The zone extends from the ground surface down the major root zone. In intermediate zone, vadose zone extends from the lower edge of soil water zone to the upper limit of capillary zone. Non-moving vadose water is held in place by hygroscopic and capillary forces. Temporary excess of water migrate as gravitational water. Whereas in capillary water, below the hygroscopic layer is the capillary fringe held in the pores by force of surface tension or capillarity. Plants receive water and most of nutrients from this fringe. The last one, saturated zone. After saturation, the excess water drains through the soil under the force of gravity and builds up the groundwater table. Occasionally, a body of groundwater will be found above a bed of impervious material. In order to understand the occurrence of groundwater and its vertical distribution, let's first consider the hydrogeological zones present in the figure. The zone between the ground surface and the top of capillary fringe is called unsaturated zone or zone of aeration, which consists of voids or pores partially filled with water and partially with air. Water is held at a pressure less than the atmospheric pressure in the unsaturated zone. The zone between bottom of the unsaturated zone and the top of the water table is called capillary zone, wherein most voids are filled with water, but the water is held at a pressure less than the atmospheric pressure. The zone extending from the water table to an impermeable layer is called saturated zone or zone of saturation, wherein all voids are completely filled with water. In this zone, water is held at a pressure greater than the atmospheric pressure, and hence it moves in a direction based on the contiguous hydraulic situation. The unsaturated zone can be further subdivided into soil water zone and intermediate zone. The zone between the ground surface and the top of water table is known as vadose zone. The Vadose zone consists of unsaturated zone and capillary zone, also known as capillary fringe. The water present in the Vadose zone is called Vadose water, which is held at a pressure less than the atmospheric pressure. While this water is still able to move within the Vadose zone due to metric potential and gravity, it cannot move out of the zone into wells, pits, or other water collection systems that are exposed to the atmospheric pressure. The term Vadose zone is technically more appropriate than the conventional term unsaturated zone, because portions of the Vadose zone may actually be saturated even though the pressure of water is below the atmospheric pressure. The term Vadose zone has become popular and is widely used these days in the fields of groundwater hydrology and soil physics. The water stored in the zone of saturation is called groundwater. Not all underground water is groundwater. Rather, only free water or gravitational water, the water that moves freely under the force of gravity into wells, constitute the groundwater. A precise and practical definition of groundwater is that portion of water beneath Earth's surface which can be collected through wells, tunnels, or drainage galleries, or which flows naturally to the Earth's surface via seeps or springs. Depths to groundwater may range from 1 meter or less to 1000 meter or more. There are also places where underground groundwater does not exist at all. So in vertical distribution of subsurface water, you have learned about various zones such as zone of aeration, intermediate zone, capillary zone, and saturated zone. So groundwater occurs in different types of rocks and soils. So here different types of rocks exist are igneous rocks, sedimentary rocks, metamorphic rocks, and occurrence of groundwater in various type of soils. The various types of rock possesses variable water bearing properties depend on permeability and porosity. In case of igneous rocks, intrusive igneous rocks are generally very compact and dense. Hence, these are non-porous. They are barren of groundwater under normal conditions. As a result, they have negligible porosity and permeability. Weathering and fracturing decreases with depth greater than 80 to 100 meter and disappears. No groundwater can be expected in such rocks at great depth. Example, granite, dolerite, etc. Whereas in extrusive igneous rocks are generally rich in cavities and contraction cracks, and as such may become permeable and source of groundwater underground water. Example, volcanic rocks, basalt, etc. In second types of rocks, sedimentary rocks, gravel possesses the highest water retaining as well as water yielding capacities. The other sedimentary rocks in their successive order of decreasing capacity are loose sand, sandstone, limestone, etc. Sandstone water bearing capacity depends much upon their texture and nature of cementing material. Coarse grained sandstone may be good aquifer, fine grained sandstone may prove to be the poorest aquifers. Whereas in case of limestones, the dense and fine grained limestones, they have no primary porosity but solution cavities and channels are common in them, which sometimes make these rocks highly porous. In case of metamorphic rocks, polluted and or lineation, if present and well developed, may contribute some porosity to metamorphic rocks. Such rocks are formed under great pressure. Primary porosity cannot be expected to be much. Among the foliated form of metamorphic rocks, gneisses are less porous than schist. Among the non-foliated rocks, quartzite has very little porosity by virtue of their compactness and granulose texture, whereas in case of soils, clay and coarser material mixed with clay are generally porous, but they are so small that they may be regarded as relatively impermeable. Clayey soils can provide small domestic water supplies from shallow, large diameter wells. In alluvial depths, water courses consist of the alluvium that forms and underlines streams, channels, as well as forming the floodplain. Wells located in highly permeable strata bordering streams produce large quantity of water. Dear students, in this session you have learned about vertical distribution of groundwater and groundwater occurrence in different types of rocks and soils. I hope you have understood. Thank you.